All right, now I'm recording. Okay, so we're going to start with problem 3, 4.1. And there's this graph that looks kind of like this. That's not the prettiest thing in the world, but okay. So this graph, they're asking us to indicate all critical points of the function and how many critical points are there, and then identify them as local max, min, or neither. Basically, if you're looking at a graph, like the first thing, like what is the first thing you would think of when I said critical point?
The lowest point or the highest point on the graph?
Yeah, so here are 2 of the lower ones, and here are 2 of the higher ones. And then you would say this is a max because these are higher.
Mm-hmm.
And this is where the derivative goes from, this is positive derivative, this is negative derivative. And then you would label these as min because this goes from negative derivative to positive derivative. You can kind of draw them in lines like that. Like if, I don't know if I talked about this in the lessons, but see, it's been a while since I've done this line thing. But so let's say this is at 0.4, and this is f prime. So here we say the derivative is negative, and here after 0.4 we say the derivative is positive. Like this 4 is very arbitrary, but the point is that you can kind of see the min, like the little like cup shape of the min. Whereas if we were to go over here, and we're going to call this 0.9, here at 0.9, this derivative is positive this whole way, but then at 0.9, the derivative switches to negative. So you can kind of see there's a max there. And basically, critical point is just the generic term for anything that is like a max or a min. This neither thing comes into play is like a kind of like a straight flat region or something like that, where it's like not clearly either a max or a min. But like I think of critical points as generic terms for max or min. So that's what a critical point is. And do you understand?
Yes.
Then this critical point is when the derivative is equal to 0, because it's going negative, 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 it zeros, there's a flat line, and then it goes positive, positive, positive. So anywhere where the derivative is equal to 0 is the critical points. So that's critical points. The reason they do this like whole like local min max thing is because they want you to be able to say like, okay, so here is a maximum, here is a minimum, here is a maximum, like this is like the local region. And did you guys talk about like absolute global, they call it global max and min? This is section 4.3.
Yes.
So the global max and min, if this is what we were looking at, if this is what the whole function looked at, and we said, okay, like this is the only thing we're analyzing, this is the global min, and this is the global max, because this is the lowest point and this is the highest point. So when it says global, I tend not to think of like, okay, like where are the critical points, like where are the maxes and mins. I always think of like what is the highest y value I can have and what is the lowest I can have. And in some instances, it will be one of the critical points that you looked at earlier. Like if it looks like this, then this is going to be the max, the global max. But in this case, both the global max and the global min are at these edges of the function. And that is because I drew these lines, these ones. I said that we're only analyzing the function from here to here.
Mm-hmm.
And so I had to evaluate the end points of this function. If I were to say very generically, this function just, I'm not evaluating any endpoints of this function, it's just kind of going into infinity, then there would be no min, because these would just go to negative infinity, both of them. So there would only be a global max here. So that's like conceptually the difference between global max and global min, and then like the locals. They call it local just because they want you to say, like, look at this graph. Is there a point where the derivative goes from being negative to positive, positive to negative? Like, what does this graph look like? It's like a means of analyzing the graph.
Okay.
So yeah. Okay, so when we have a problem like problem 16, also 4.1,
Okay.
this is basically what a lot of these problems are going to look like, because they're going to have you like use a lot of the skills that you have been like building for this like semester so far. Because you start off and they say, like, this is your function, like find the local max and min, and then it says check your answer by graphing, but we're not going to do that because I don't really have much capability to do that right now. So this is our function. We don't really know what it looks like right now, but we're trying to find the maxes and mins. First thing we're going to do is take the derivative. So what's the derivative of this?
12x cubed minus 12x squared.
Mm-hmm. That's it. Okay. So we are going to say this is the derivative. I know that critical points are when the derivative equals 0. So what I'm going to do is I'm just going to set this whole thing to 0. And then I'm going to do some algebra. I'm going to pull this 12x squared. So this is x minus 1 equals 0. And so one of these can be true. X can equal 0, because if x equals 0, this term equals 0. And x can equal 1, because 1 minus 1 would be 0, so this whole thing would be 0 as well. So I look at it in terms of these terms to make it easier for myself. I say, what can make this term be 0 and what can make this term be 0? And it's an either or thing, because if one of them is 0, the other one doesn't have to be. So x is equal to 0, 1. And this isn't like a point. It's literally just x is equal to 0 or x is equal to 1. Oops. So I'm just going to write that more explicitly. And of course, it can't be this. So these are our critical points. This is part 1 of the problem. We found our critical points. Then we're going to use the first derivative test to determine whether they are local maxes and mins. Let me quick look at what the book wants you to do for first derivative test. Okay, so basically the way that I would do this is I would draw a line like this. And I would say this is, like, this represents my x-axis. This is point 0, this is point 1. This is -1. It doesn't need to be like perfect, like in terms of, you know,
Scale.
yeah, that's the word. Because I'm just kind of using it as like a means of figuring out like what's going on. And I picked these points in between. I picked -1 because it would be easy to evaluate, and I picked -1/2 because it was something that was easy to evaluate between 0 and 1, and then I picked 2 because it was something that was easy to evaluate that was above 1. Theoretically, I could pick 10, 100. It doesn't really matter what number I pick as long as it's above 1.
Okay, hold on. So this should be a half, not -1/2 then.
Yes, it should be. Sorry. Okay, so 1/2. Okay. So basically what I'm going to do with this is I'm going to figure out what the derivative is at each of these points around the critical point. Because I know if I plug the critical point into my derivative, I'm going to get 0. Because that's how I found that those are the critical points. So I'm going to take f prime of -1, f prime of 1/2, and f prime of 2. And I'm going to find out what each of those are. So I think it's easier to put it into this version. This f prime of x is equal to 12x squared x minus 1. But whatever works for you. So this is 12. -1 squared is 1 times -1 minus 1. This is 12 times -2 equal to -24. And all I really care about here is whether or not it's positive or negative. This is negative. So at x is equal to -1, I know the derivative is negative. So I'm just going to draw it like a down arrow. You can also draw it just as a negative sign. Then I'm going to do the exact same thing. This is 1/4 times 1/2 minus 1. So this is 3 times -1/2 equal to -3/2, right?
Yes.
And this is going to be 12 times 4 times 2 minus 1 equal to 48 times 1. Okay. So we have negative there. And then we have so there's this weird little jump thing happening here where it's negative and then it's negative again. And that is going to look something like this. There's like a flattened area where the derivative is equal to 0, but there's no change in the direction of the derivative on either side. This, however, derivative goes down, derivative goes up. That is a minimum. So yeah. And like the book just says, like, if f prime changes from negative to positive at the point P, then f has a local minimum at P, which is, I don't know. I feel like this is more intuitive because I like to see it like drawn. I like to see it going down and then back up, but that's me. So that's how you would approach a problem like this. It's a lot of just kind of like doing crazy things, but yeah. Another thing, just to make problem solving easier, is the reason you don't have to solve all of this stuff. You can just say 12x squared x minus 1. If x is equal to -1, then this is positive. and this is negative, so positive times a negative is equal to a negative, because all you care about are the signs, really. You don't really care about what the actual derivative is. So any way that you can find the signs reliably is a-okay.
Okay. So what about the point at 0? It's just going down, so there's no change right here. That's what you were saying before, right? Mm-hmm. Okay.
So here is kind of what it looks like. So this is kind of a flat region here. And at this point, the derivative is equal to 0. But it goes down, and then it still goes down. So this is 0. And there is no change in the derivative. If theoretically we had something going up, then there would be a min. Or if this originally was going up, we'd have a max. But because it's down and then down, there's a flat region. Which is one of the most conceptually hard parts about critical points, I think, is that how something can be neither min nor max. Honestly, I would just say take it and try to internalize it, because I don't really have a good explanation for what's up.
Okay.
But other than flat area thing, it's check on page 178, figure 4.4, right at the top of the page. That's kind of what it looks like.
Okay.
Are you good with the second derivative test?
Yes, that part is okay.
Inflection points.
I think I had a question there that I was having a hard time with. I'm trying to see. Can we do a question from there? I don't see. I was having trouble.
Okay. Let's start with, let's do number 1. Which is basically how many inflection points are there?
Oh, this one. No, it's one from, there's 2 chains. So there's one on either side right there. And yeah.
So yeah, because here it's concave up, here it's concave down, and then here it's concave up. So the way that I see it, there are 2 different ways to look at inflection points. One is in terms of the greater graph, is it concave up or concave down? And the second is in terms of what is the derivative doing. And I kind of look at it in that direction, just because that's the easier way for me. I say here the derivative is small positive, it's getting more positive, more positive, more positive. Here it's the most positive, and then here it gets less positive, less positive, less positive as it approaches 0. And so I say this is the point where it's the most positive, and this is the point where it's the most negative. But that's just kind of like, I don't know if I'm doing like a great job of explaining that, but I like to see, like, if I were to draw all of the tangent lines along there, like what would the change be? Like how would they look in comparison to one another? So that would be the inflection point. Okay. We find inflection points by saying that the inflection point is where the second derivative is equal to 0. Because the second derivative is the rate of change of the derivative. So if I were to look at this and this exact same, and say, okay, so here I have positive derivative going up, then it becomes less positive, and then I hit 0, and then it goes getting more negative, and then it's less negative, and then eventually it's going to hit 0 again. This is what the original looks like. This is a graph of the derivative, where I'll mark out the same points. This is the inflection point. This is this is the max, and this is the min. Okay. So if you graph it out like this, you can see very pretty clearly that, okay, so this is my maximum point. It's right here where my derivative is equal to 0. So that's why my critical point is equal to, critical point is where first derivative equals 0 works. But these inflection points have moved. They've moved. This one is now at a max, and this one is now at a min. And if I wanted to find out exactly what like numeral, like x is equal to what these are at, I have a way of doing that, and it is to take the derivative again and see where they're at. Because if I were to take the derivative of this shenanigan, so this is, it's positive, it's becoming less and less and less positive as you go. So it goes something like this. And then it goes negative. And it hits its most negative, and then it becomes less negative, and then it hits 0. And then it's positive, and it's positive, and stuff. So this is kind of what the second derivative is going to look like. And this point is right here, and this point is right here. So these points may remain the same for this entire process. Like this x equals is the same as this x equals. And so we're going to use this to find out what x actually equals. Like at what point in time does that equal 0?
So, yes. Okay, so my question is now that where you have the inflection points on the original graph, when you put it on the second derivative, those both equal 0?
Yep.
Okay. Okay.
Because they get, it's kind of like a transference process. Inflection points in this graph become maxes and mins, and maxes and mins become 0.
0. Okay.
And then you can basically do the same thing again. Maxes and mins are going to become 0. And there are no inflection points in this. Actually, there are. That's a lie. But, what's that? Yeah, this would be an inflection point, but because we have a min down here. But we're not worried about that because we already know what x value that is. So it's basically like a transference of like, okay, like how can I best analyze to figure out what point this is actually happening at. let's do 14. So 14 is going to look like this. Okay, what is f prime going to be?
8x
This
squared.
is a 2.
6, sorry. Cover the other one. 6x squared plus 6x minus 36.
Okay, so now we have our derivative, and we can go through and do all of our critical point stuff. We can say that f prime of x is equal to 0, and we can say that, let's see, we can, the way that I would do this is to factor out the 6 first. X minus 6. And then I would divide it further. I would say this is x. What is this? X plus 3x minus 2. That's squared plus 3x minus 2x minus 6. Okay, so that works. Okay, so this is the same thing as this, right?
Yes.
Okay. All right. So we're going to find where that is equal to 0. 6 cannot equal 0. If x is equal to negative 3, then this term is equal to 0, so the whole thing is going to be equal to 0. And if x is equal to 2, this term is equal to 0, so this whole thing is equal to 0. So we have our critical points at x is equal to negative 3 and x is equal to 2.
Okay, so if we had factored out like 6x, then that's when that would have equaled to 0 too.
Yes.
Say if there was an x out there, yes.
Yeah, if we didn't have this 36 here, so if that was gone, we could say 6x times x plus 1. And we could say x is equal to 0 or x is equal to negative 1.
Okay.
But because we have the 36 there, we have to factor it in. Okay. Then we do what's next. We draw our line. We have a point at negative 3. We have a point at 2. I always find it easiest to just look for 0 if I have a gap like that. And then I'm going to do, I don't know, the 3. I'll do negative 5. So this is going to be positive. If I'm doing this at negative 5, it's always going to be positive this. Negative 5 plus 3 is a negative. Negative 5 minus 2 is negative. So positive times a negative is going to be positive. Right?
Yes.
So I'm going to do it again. I'm going to say at 0, this is positive. I'm sorry, I'm kind of like blocking this, but this is positive. And 0 minus 2 is negative. So a positive times a negative is going to be negative. And then this is positive. 3 plus 3 is positive. 3 minus 2 is positive. This is again going to be positive. So I have a max and I have a min. I have a max at x is equal to negative 3, and I have a min at x is equal to 2. Right?
Yeah, so this goes down. Okay.
Okay. So next we're going to find our inflection points, and then we're going to be done with this problem. So we have f double prime is equal to, what is this equal to?
So that is 12x plus 6.
Mm-hmm. So we're going to say f double prime is equal to 0. I'm going to factor out the 6. So x, when x is equal to -1/2. One way that you can do this is you can separate it out. You can say 2x plus 1 is equal to 0. 2x is equal to
-1.
Yeah. But
X. Mm-hmm.
So this is what we have. That's where our inflection point is. Our inflection point, we can like use this to actually draw a graph now if we wanted to. Because we know we have, this is -3. We have a max here. This is it's -1/2. I lied. That's positive. So if this is -1/2, you know, this is where the inflection point is. And this is 2, where the min is. So we have max, inflection point, min. And we can tell the inflection point is, this is kind of poorly drawn. The inflection point is where it transitions from concave down to concave up. What are your thoughts?
Like, it's much clearer now. Like, I thought I'm using the line graph before, but I just did not understand it. Like, it just wasn't clear to me. So like now this gives like a better picture of what's going on. But because before you just saw the numbers and then you said I'm plugging the numbers and you're like, wait, why are you doing that?
Like big, like magical.
Yeah.
I like to see the arrows and stuff like that because it like gives me the visualization that I need. So yeah. We talked about global maxes and mins. Do you want to do one of those problems or?
Yep. Yeah, that would be good. Let's go to.
So. Okay.
I think that was the section like I had the most problems and like I got lost.
Okay. What kind of problem are you looking at?
I'm 4.3. I know I didn't get through 31. And then there was 35 and 37, but I think Kasha did those afterwards. But we can just pick one of the first one and then can do 31 too, if you don't mind.
Yeah. Okay, so are you having difficulty with like sketching a function like that has certain properties, or problems like 16 where you're essentially like doing everything?
All right, so 16. Yeah, can we, yeah, 16 is good. Can we do that? Yeah, it's
16 is like very much an example of a lot of the problems that they'll like to put on the test, because it's something that like tests everything that you've done. So part A is to find f prime and f double prime. So we have f of x is equal to x cubed minus 3x squared. So I'm just going to go ahead and I'm going to find f prime, and let's find f double prime right now.
okay.
So f prime is going to be 3x squared minus 6x, and f double prime is going to be 6x minus 6. So these are the functions that I'm going to be using to solve this problem. Okay. Part B, find the critical points of f. Critical points are equal to 0. So I'm going to say 3x squared minus 6x equals 0. I can factor out a 3x. So this is x minus 2 is equal to 0. X is equal to 0, or x is equal to 2. And you see how I get that?
Yes.
Okay. So these are my critical points. So this is part B. Find inflection points. F double prime x is equal to 0. So 6x minus 6 equals 0. I can do 6x minus 1 is equal to 0. X is equal to 1. And that's my inflection point. Correct?
Yes.
Okay. Part D, evaluate f at its critical points and at the endpoints of the given interval. Identify local and global maxima and minima of f in the interval. Okay. So this is the point where it kind of becomes a little bit of a doozy. So what we're going to do is we're going to we can do this line, but we are going to need to find what f, the original f of these critical points is. What is f of 0? F of 0 is going to be 0. F of 2 is going to be, oh, I screwed up. First, we should check our, very important, we have an interval for this function, so we're only analyzing it between -1 and 3. If, for instance, I had a critical point of x is equal to 4, I don't, but if I did, I would just discard that because I don't even need to like consider it because it's outside of my interval. I don't, so that's good. I'm doing everything okay so far, but just like make sure that you're like in tune with what is going on with the interval. So, f of 0 is equal to 0. F of 2 is going to be equal to 8 minus, let's see, that's 3 times 4, 12 is equal to -4. Okay. I'm also going to find f prime of 0. F prime of 0 is going to be, oh, not 0. I'm going to do f prime. See, you always like know when you screw up because f prime of 0 is 0, and I just got very confused. So I should find f prime of -1. I should find f prime of 1. And I should find f prime of 3. -1 is going to be -3 times -3. That's positive. Of 1 is going to be 3 times -1, so that's negative. And then of 3 is going to be 9 times 1, so that's positive. So here is my 0, here is my 2, positive, negative, positive. So I got a max at 0, I got a min at 2, min at 2. And now I know exactly what those points are. I know that at 0, 0, this is a max. And this is an ordered pair. And I know that at 2, -4, this is a min. I'm not done yet though, because I still have to figure out if there are global maxes or min. So this is from my critical points. This next step, I have to figure out f, just plain f of -1 and just plain f of 3. Because
okay, so hold on before I get you to the next point. So when you do just f of x, those you're finding the points, the first set of points, and then f prime tells you the whether it's positive or negative. Okay. Okay.
And you can do this in any order. You could say, okay, I know 0 is a max value and I know 2 is a min value. Just make sure that these correspond with this, because if just like I don't know, make sure that what you get here are reasonable.
Okay.
So yeah, so f of -1, this is -1 minus 3, so this is -4, and this is 27 minus 27, right?
Yes.
So that's 0. So next step is I'm going to kind of sketch out this graph, and I'm going to ask myself what's going on with it. So here is negative, that's a lie, I don't know what that is. This is -1. And I know that f of -1, the point, -1, -4. And I know there's a point that is 3, 0. So I am going to graph -1. This is going to be -4. I'm going to graph 0, 0. I'm going to graph, this is 1, 2, 2, -4. And I'm going to graph 3, 0. So I'm like trying to draw this function out. And I know that there is an inflection point at f is equal to 1. So this goes like this. Sure. And this restriction up here basically says that I'm cut off right here. I don't care about anything that happens outside of these lines. My inflection point, if I were to look at where things are, this would be concave up. That would not be concave up. That would be straight, it looks like.
Yeah, they all kind of.
So that would be straight.
Like a straight line, yeah.
So that's not concave up. This is concave down because this should have a bit of a curve to it. And then this is also concave up. So there's one point where it changes, and it's right here at x is equal to 1. And that's where it switches from being this concave down to this concave up. And then part E is graph x, which is what we just did here. So our global max is going to be 0. And our global min is going to be -4. And each of these have 2 different points where things are equal to that, but we're just looking at what y value is the highest and what y value is the lowest.
Okay.
So yeah. These are a favorite problem, again, just because they test everything. So I would do a bunch of these just to get good at figuring out what's going on. I'm still not the best at putting all of this information together. Sometimes I just totally mess up. So it's it's a skill that you have to work pretty hard on.
Okay.
But you can do it. I believe in you.
And that's
And then you wanted to do 31.
yes, 31.
Okay. So find the exact global maximum and minimum values of the function. The domain is all real numbers unless otherwise specified. So ft is equal to t over 1 plus t squared. This would be, we'd use the quotient rule. So we'd say f is equal to t, f prime is equal to 1, g is equal to 1 plus t squared, g prime is equal to 2t. And the quotient rule goes f g prime minus f prime g, right?
Yes.
Yeah. All over g squared. So this would be t times 2t minus 1 times 1 plus t squared all over.
Wait, isn't it f prime g and then f g prime? Or
Yeah.
does it matter? Yeah.
You're right. You're right. I screwed it up. Okay. Okay. So it's f prime g minus f g prime all over g squared. So it's going to be 1 times 1 plus t squared minus t times 2t all over 1 plus t squared. So this is going to simplify out to be 1 plus t squared minus 2t squared all over 1 plus t squared 1 minus t squared over 1 plus t squared. So this is prime t. So then they want you to find the global minimum and maximum, And in this case, we don't have any end values to evaluate, so we're just going to find what the minimum and maximum are of this function. So first, we're going to find the critical points, because we have a derivative, and we know we can find critical points where the derivative is equal to 0. So this is 1 minus t squared over 1 plus t squared squared. And we know we can't have a 0 in the denominator. So as a little side thing here, we're going to say that if t squared is equal to -1, then we can't have it, which is not possible with the numbers that we have, so this is fine. There's nothing like keeping us from figuring out what's going on here. All we need is this numerator to equal 0.
Okay.
So if the numerator equals 0, the whole thing equals 0. And that is going to be 1 is equal to t squared, because this equals 0. So t is equal to plus 1 minus 1. So we have 2 critical points. T is equal to 1, and t is equal to -1. Are we good so far?
Okay, yes, yes. So you don't have to worry about what's going on in the denominator.
Yeah, I mean, if you have 0/4, you have 0.
0.
It doesn't matter how many things you split it into. So you just have to make sure that the denominator isn't like illegal, because if you have 0 in the denominator, then you've done bad things. So if the denominator equals 0, you got bad things. But because that's not possible in this situation, you're a-okay.
Okay.
Unless we wanted to get into imaginary numbers, which we decidedly don't. Okay, so we have these 2 critical points. We're going to go all the way back, and we're going to say f of -1 and f of 1. And so this is going to be -1 over 1 plus 1. And this is going to be 1 over 1 plus 1. So this is going to be -1/2, and this is going to be +1/2. So we have these numbers here. We still need to figure out what's going on with the mins and maxes. So we have -1, 1, let's find 0, -2, and 2. F prime of -2, F prime of 0, and F prime of 2. So F prime of 0 is going to be 1 over 1, so that's just 1. Of -2, this is 1 minus 4 over 1. 1 plus 4 squared, and so this is going to be negative, because it's going to be a negative divided by a positive, so it's just going to be negative. And for 2, it's going to be 1 minus 4 over 1 plus 4 squared. Again, this is going to be negative. So we have negative, positive, negative. This one is positive. At -1, we have a min. And because the only value we have is this, we're going to assume this is the global min. So global is equal to -1/2, and the point is -1, -1/2. And then the global max is equal to 1/2. This is at 1, 1/2. And we're assuming that based upon the evidence that we have, this function is not going to ever have a y value that is above 1/2 or below -1/2. So it's got a really small range. thoughts?
All right, so because you only had 2 points when you checked it out, like if T was say 2 for the first one, and then if the critical points were like 2 and -2, you will still only worry about just those 2 points, right?
Okay.
For the global max and the global min.
Give me 1 sec. I think. Okay.
I think the question I'm trying to ask is that, does the global max and the global min have to happen at the critical points?
No, but we don't have any side like views to narrow it down.
Okay.
Because we can assume that because there is no larger point, like this is what the max and this is what the min are. Let me share. Can you see my screen now?
Yes.
Okay. So do you see this graph right here?
Yes.
That is the graph of this function.
Okay.
And it's not going to go below. Its like lowest point is going to be -1/2, and its highest point is going to be 1/2. And it's just going to, oh, I don't have Wolfram Alpha Pro, but it's just going to continue on like this for eternity.
Okay.
It's never going to go higher or lower. Okay. Let's see. Let's go back to, oh, it's saved all my stuff. So.
Okay. I get it now.
Cool.
I think I'm okay over that one now. Can you do 36?
53, 36. Okay. So if you have 100 feet of fencing and want to enclose, oh my gosh. This is, I hate optimization.
They gave us 35 and 37, and I was looking at it, I was like, I don't even know what to do with these now.
Okay. So if you have 100 feet of fencing, 36, and you want to enclose a rectangular area up against a long straight wall, what is the largest area that you can enclose? Oh man, it's been a hot minute since I've done any optimization problems. Give me a sec. Okay. Section. Oh, he's the bane of any calculus student's life. Like, no offense to optimization problems, but ouch. Okay. So.
Well, I didn't see any on the test I did. I don't know if there's any at all in the actual second attempt or third.
Dude, I hope not. I hope if they haven't specifically told you how to do this, that you don't have to do this.
Okay.
I'm wishing the best for you.
They gave us 35 and 37, but it never showed up on the test I did.
Okay.
Nothing to that extent.
Basically, how you do. Oh, go ahead.
And for the midterm, there's nothing that's gonna come on that. The midterm is actually gonna stop at chapter 3.
Yes. Okay. So that's good.
Yes.
In my opinion, these are the worst. So basically what you need to do is you need to look at this, and then you need to like come up with your own function, and then you need to find like how to like maximize or minimize like what's going on with this function. And so if you read this, you're like, okay, so I want to maximize my area. So I'm like literally gonna write this down. Max area. And so I need, and like in order to do this using what, like the problem solving tools that we have, I need to find A and A prime. So I know area is equal to length times width. And we have a long straight wall. We have, okay. Oh, we have two functions. That's what's going on here. Okay. So we have area is equal to length times width. And then we have 100 feet. And so let's like draw this out. We have this wall. And then we're going to have fence. And this is like the entire area in between. So this is going to be width, this is going to be length, and this is going to be width again. So 100 feet of fence, we're going to have one width, one length, and one width. And then the rest is going to be the wall. So 100 is equal to 2 width plus length. And we're basically going to solve for one of these to be able to like get rid of one of these variables. So I'm going to say that length is equal to 100 minus 2w. And then I'm going to go and I'm going to put this in this equation. So I have A is equal to 100 minus 2w times w. So I'm going to simplify this out. I'm going to find A prime. And then I am going to find where A prime is equal to 0. Are you following me up to this point?
I am.
Okay. So A prime is going to equal 0. This is 100 minus 4w. So minus 100 is equal to minus 4w minus 4 minus 4w is equal to 25. Okay. So area is going to like, okay. So you can't like have a graph that like best explains this in like that like logically like you can like pull out of like this equation, the equations that we have. So basically we have this area function, and there's going to be a point at which area is maximized, and then a point at which okay, I'm gonna try to, I'm not gonna like draw the graph, but if we were to have a graph, it would look like this. So there is a width, like pretend it looks like this. It doesn't look like this, but pretend it does for the sake of simplicity. There's a point at which this width gives the max area. So we're looking for the biggest area. And we have this condition, is that there's only 100 feet of fencing. So we have this point. We are going to do our line thing where we say, is this a max or a min? I'm assuming it's going to be a max, but we just have to make sure. So let's do 0 and let's do, I don't know, 30. So a prime of 0 is going to be 100. And a prime of 30 is going to be -20. So this is a max. So I know I have a max at W equals 25. And that's a max of my area. So basically what I'm going to do is I'm going to say W is equal to 25 when my area is maximized. So I have 100 is equal to 2 times 25 plus L. And then I solve for L. And so this is 50 plus L. L is equal to 50. So my dimensions are going to look like this. I have my wall. I have 25 feet of fence. I have 50 feet of fence. And then I have 25 feet of fence. And this is how to maximize my area inside. If I were to have something that was different, if I were to have this wall and then I have 1 foot of fence, 98 feet of fence, and then 1 foot of fence, my area would be much smaller. So that is it. That is how to do this problem.
Okay. Now I kind of understand much better what they were trying to ask.
Yeah.
They're just words and they're like, what is this?
They want you to pull an equation out of nowhere. Not out of nowhere, but the trouble is to find the equation. All of these optimization problems, the biggest issue is going to be finding what equation to use and getting all of the information you need in there. So I would recommend you start off with what you want written down very clearly, and maybe also write down what you have. Say you have 100 feet fence. You have the wall, so you know you only have 3 sides. Like write down what you know in order to figure out like what you can do to figure out what you don't know. But yeah, it's roady.
Okay. All right. We can move on to 4.4 now.
Okie dokies. So this is basically talking about like applying this to like profit, cost, and revenue. When we were doing like marginal cost, we said that like that was like the derivative of like the cost. And so if we had like a marginal cost of like 1, let's say at quantity is equal to 10, we know that our marginal cost is equal to 1. So the cost of producing 11 costs the cost of 10 plus 1. That's the marginal cost. So basically, we're just going to like be applying these further using our maximum and minimum ideas. So we're basically just going to be finding maxes and mins, but using the language of marginal cost, marginal revenue. That's what do you want to do number, oh, this is just estimating.
The hardest part for me, and one question did come on the task too that I didn't, like after looking at it, I just didn't get what they were asking, is when they draw the graph and then they pick a point on the graph and it's like look at question 4. It was something similar to that,
Okay.
but rather than where Q1 is, the point was like further down, like halfway through.
Okay.
And it was asking, I think I wrote it down, what is going on at that point below Q1.
Mm-hmm.
And I just never got it, because I think it was saying that at that point marginal cost equal marginal revenue, but I just couldn't see that because the cost curve was over in the revenue curve. So
Mm-hmm.
how would it be equal?
Well, marginal cost and marginal revenue refers to the slope of the lines.
Yes.
So on 4, that's really atrocious. Sorry, my pad got turned. Okay. So that's still pretty bad, but we're gonna have to live with it. This is our revenue curve, and our cost curve looks something like this. If I could turn this, it would be better. This is all just very poor. I'm so sorry. That's not an eraser either. Okay. There, that's flattish. This is cost, and this is revenue. The thing is in the book at Q1, the marginal cost is equal to 0 because this slope is 0. I'm gonna draw this a little bit better. So this slope is equal to 0. So marginal cost is going to be equal to 0 at Q1. At Q2 or at Q1 also, the marginal revenue, this is a line, so the derivative is always just going to be one number. So marginal revenue is some number. We don't know what that is because we don't have anything like more specific than this. At Q2, which is right here, marginal revenue is that same number.
That same number at Q1?
No, at marginal, yeah. So marginal revenue is the same at Q1 and at Q2 because revenue is this line here. So the slope of the line, if this line, for instance, had the equation 4x, the derivative is always going to be 4. So, okay. And then the cost at this point, let's look at this. That looks pretty dang positive. So the marginal cost at Q2 is pretty positive. So that's how I would like start going about analyzing this. Okay, so it wants you to draw the total profit, the marginal cost, and the marginal revenue to solve this problem. So basically what you're going to do, I'm going to call okay. So my marginal cost starts going positive, approaches 0. So starts positive but approaches 0. It hits 0 at Q1. Then it starts to become more positive, and it becomes very positive. And this is Q2, and we don't know what happens after this. So this is going to be my marginal cost because derivative of the cost is 0 at Q1, and at Q2, it's pretty positive. Marginal revenue is going to have the same the entire way down because it is a line. So the derivative is just going to be a flat line. And so this is going to equal whatever number. So profit is equal to revenue minus cost.
So you're just like combining both graphs.
Yeah.
Under one. Okay.
Basically. So at point Q1, we know that revenue is equal to cost because that's where they're intersecting. So revenue is equal to cost at points Q1 and at point Q2. I'm going to move this up because we need to be able to get into the negatives because there are some points with negative profits. So let's do this. So Q1, Q2, profit is equal to 0 because cost is equal to revenue, right?
Yes.
Before that, cost is greater than revenue, which means it'll be in the negative somewhere. And what we have going on is we have this constant revenue stream, but the cost is increasing, and then it's not quite as increasing, and it's approaching 0. So actually, it isn't increasing. The cost is just approaching 0. So we have whatever revenue we have, and then we have the cost, and the cost is gradually approaching 0. So we're just going to have this relationship here. Then between Q1 and Q2, cost is below revenue. So we're going to have a positive profit. And so the cost starts off about the same as the revenue, drops pretty low, and then gets closer and closer and closer to the revenue, right?
Yeah.
So low cost, higher revenue, low cost, high revenue, higher cost, high revenue, higher cost. Now they're the same. And then again, cost is going to be greater than revenue, so it's going to plummet down again. So this is what the profit is going to look like. We can, in addition, find what the marginal profit is, or the derivative of the profit, and that is going to be, I lied. It's going to be aligned with the negatives. Where this is Q1 and this is Q2. Because this is positive, 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 negative, 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 negative. So Q1 is going to be about right here. Q2 is going to be about right here. The place where the profit is maximized is right here. This is the biggest profit that we can possibly have, this point right here. That is where the marginal profit is equal to 0. All that jazz. So that is problem 4. Thoughts?
All right, so I'm still soaking this one up. Okay, I think I kind of understand it a bit better now. But I just didn't get that point where it's like the cost and the profit are equal, even though it wasn't like crossing each other.
Yeah, I'm not sure what that problem was.
Okay.
I guess without seeing it, I couldn't really.
Yeah, I know, and yeah, you have to actually see it to see what I'm talking about, but it more looked like 4 or 1, and
Okay.
it's like just in the region after it was crossed. But for the most part, 4.4, I understand it much better than the other 3. This one was
All right.
okay. This one isn't too bad.
Awesome. Okay.
Yeah.
Any more questions?
No, I think I'm okay now. I
All
feel
right.
much better now. Yes.
Awesome. Okay. I will make a post to make sure that everybody knows that we'll have another session next Sunday as kind of a review slash like what's going on.
Yeah, because the thing was that I thought the review would be on Sunday, and then we'll just do the regular chapter stuff this week.
Oh.
Because Professor Stan made a post, and he said that next week would be like the review. But I didn't even think that you would have had a class next week because it's still part of spring break.
Yeah.
Class really starts back on Monday.
Yeah. Yeah. I don't
So,
know.
but then he made a post, and then he said Kasha would be doing something on Friday too.
Mhm.
So this coming Friday. So I'm not sure, but
Okay.
yeah, just let us know. There's gonna be a class.
Yes, for sure. For sure. Make a post. Okay.
All right.
Yes, you
Thank
have a good
you
one.
so
Have a good
much.
break.